Is my screen visible to you?
Yes, sir.
Fine. Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Present, sir.
Ananta Kumar,
Present, sir.
Arnachalam,
Sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan.
Sir, just went for bio break. He's here only in the conference room.
Okay.
Yes.
So once he come back, he can confirm.
Sure, sir. Sure. In 2 minutes, sir. Before the
Prabhakaran?
roll.
Present,
Okay.
sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Roshan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijayaraj,
Yes, sir.
Vikas,
Present, sir.
Vivekanand, Yadav,
Yadav absent, sir.
Yuvraj.
Present, sir. Present, sir.
Okay. So Vivekanand and Lakshmi Narayanan have not answered.
Lakshmi. Sorry. Sir, Lakshmi came.
Present, sir.
Okay. Okay, then there are two absentees, Vivekanand and Yadav. Okay, fine. Welcome back. So we are in chapter 3. We are discussing SI and CI engine combustion in this chapter. So far, we discussed about SI engine combustion. In the last class, I discussed about the combustion chambers for spark ignited engine. Under this topic, we discussed what are the criteria, major design criteria, when we talk about the chambers, combustion chambers for SI engine. So there are three considerations. One is improving the power output from the engine. Thermal efficiency should be higher, and combustion even should be smoother without any abnormal or knock. Right. So all these are dependent on how we design the combustion chamber in terms of fixing the locations of intake and exhaust valve, spark plug, also fixing the shape of the piston and cylinder head. So we have discussed how we can improve power output, thermal efficiency, and how we can have a smoother combustion based on the combustion chamber design. After this discussion, I have also shown typical combustion chamber shapes that are available for spark ignited engine. Okay, so with that, I close SI engine combustion topic. Now I am going to start with CI engine combustion. So for compression ignition engine combustion, the discussion, the sequence of contents that we are going to follow are exactly same as what we have done for spark ignited engine. The same sequence of contents will be followed to understand the combustion process in CI engine. I'll first provide an overview of CI engine combustion process, followed by a discussion on the stages of CI engine combustion. Then I will bring out the various factors that affect the different stages of combustion. Okay, so after this, I will discuss about abnormal combustion in CI engine and what are the combustion chamber designs that are available for CI engine. So these are the contents we are going to discuss in CI engine combustion. I am going to get started with the overview of combustion process in CI engine. So this compression ignition engines, commercially they are referred as diesel engine. Since these engines are fueled by diesel, they are commercially referred to as diesel engine, which works on compression ignited engine, compression ignited principle. Okay, so this is a formal way of defining this category of engine, compression ignition engine. Commercially, they are referred as diesel engine. So these diesel engines are most versatile internal combustion engine available today. This is most versatile because you can, as you know, you can design a diesel engine with 3 kilowatt rated power. You can also design diesel engine with 30,000 kilowatt rated power. Okay, so you can see the range at which you can design this category of internal combustion engine from 3 kilowatt to 30,000 kilowatt. Small off-road engines that we use for agricultural water pumping applications are having a capacity of 3 kilowatt. Large locomotive or rail engines, okay, they typically have a capacity of 30,000 kilowatt. Marine engines typically have around 20,000 kilowatt capacity, such a large engine, okay. So you can design a small engine generally used for off-road application, and then a large engine, right, of 30,000 capacity. That's why this is the most versatile and the most popular internal combustion engine in terms of commercial application segment. In automotive segment, they are primarily used in heavy, medium to heavy duty segment. So this medium to heavy duty is based on the payload of the vehicle, as you know. Okay, they are used in passenger car, and they are also used in trucks, heavy trucks, buses, lorries, and trucks. Okay, these are the popular automotive engines powered with the compression ignition engine principle. So the major reason why this category of internal combustion engines are popular are two reasons. One is they are having a better fuel economy, much better than a typical SI engine can give. Can anyone tell me how the fuel economy is much higher or better in CI engine compared to SI engine?
Because we are running it very lean, and
Okay.
because of high compression ratio, the thermal efficiency is very high compared to SI.
So you are saying two reasons. One is compression ratio is high. It is lean burn.
Right, sir.
So lean burn, when I say lean burn, fuel air equivalence ratio is lean, less than 1. We already discussed all this in thermodynamic analysis of IC engine. So this is lean burn. The advantage in having a lean burn engine is heat loss will be considerably less when you burn under lean conditions, that is P less than 1, because you have excess air. This excess air present in the cylinder will prevent temperature rise. So operating temperatures of CI engines are much lower for a same capacity. So when you compare SI and CI, you need to compare it under similar condition. Then only the comparison is fair. Under similar rated power condition, the operating temperatures of SI engines are generally much higher because your phi value for SI engine is phi1 or phi around 1.1, slightly richer stoichiometry. It's going to result in very high operating temperature. Whereas in CI engine, it's always less than 1, typically 0.4. It varies 0.4 to 0.8, much lesser than 1. So you always have excess air. This excess air present in the engine cylinder reduce the operating temperature. Since the operating temperatures are less, the gradient for heat loss is less. Because of this, you are getting thermal efficiency benefit. So that's the advantage in having a lean burn combustion compared to stoichiometric combustion or rich combustion. Okay, and the other reason is, as you rightly said, Rosen, this compression ratio of CI engine is generally around 2 times higher compared to SI engine. SI engine typically run with compression ratio of 8 around this number, and CI engine generally have a compression ratio of around 16 or above this, right? Well above this. So it's almost 2 times higher compression ratio that we have for CI engine. This will definitely benefit thermal efficiency. You know, from thermodynamic analysis, efficiency is a strong function of compression ratio. Higher the compression ratio, higher will be the thermal efficiency. Okay, these two reasons result in high thermal efficiency that will directly reflect in the fuel economy or mileage that the vehicle gives. The mileage given by diesel powered vehicle cannot, SI powered vehicle cannot be compared with the CI powered, right? So SI engine will be out in terms of mileage. Okay, CI engines gives better mileage. This is one of the important reasons for commercial application, wherein mileage or fuel economy will come at the forefront before we buy any vehicle. Okay, as an end user of vehicle, they always look for this. This is one of the reasons why they are so popular. This diesel engine, they have a very high thermal efficiency, better fuel economy because of that. This is one reason. Second one, fuel cost, running cost is less. Fuel cost of diesel, you know, it's always lower than gasoline. Now, can you tell me why we discuss how these fuels are produced in chapter 1?
Because the processing required for diesel is a little high, little lesser than the gasoline because it's a high distillate of crude oil,
Heavy distillates.
heavy distillate. Yes.
Heavy distillate. So refineries do lot of processing for gasoline or petrol because they need to improve the octane number. Okay, so to improve octane number or antenna quality, the refinery processing involved is high for gasoline or petrol compared to diesel. This is one of the primary reason why the cost of diesel is always lower compared to gasoline, although both are produced from crude oil. The source is same, right? But the refinery processes are different. Refinery processes are less intensive for diesel. That's why it's operating. The final cost of the fuel is considerably less compared to gasoline. Okay, and other reason, density of diesel is always high compared to density of gasoline. This will give benefit in terms of mass that you inject into the cylinder. So you use a heavy fuel, diesel fuel. This also will reflect in fuel economy. We already discussed about the effect of density and engine characteristic. One of the important effect is it will improve the fuel economy. So diesel being a heavier fuel will provide fuel economy benefit because for a given volume you meter, the mass that goes into the cylinder is always high compared to gasoline. So you have to burn more gasoline to get the similar power, okay? So these are the reason why this category of IC engines are more popular in different segments, including off-road stationary applications as well as on-road automotive application. You have a wide range of engines, wide range of power output that are available. Okay, these are the primary reason why this diesel engines are more versatile compared to SI engine. Nevertheless, you have limitations also in this category of engine. So these are the limitations of this particular category of IC engine. Diesel engines are heavier compared to SI engine. SI engines are always compact compared to diesel engine. Why it is heavy?
Due to the higher compression ratio.
For the same reason. Exactly. So CR, compression ratio is high. When you have a high compression ratio, you are going to have high mechanical stress. Okay. Mechanical stress is dependent on the compression ratio. So the components have to be heavy in order to withstand the mechanical stress. So you have a heavier component, okay, adding to weight. Any other reason?
Sir, lower equivalence ratio because of which we'll have to have higher CC.
Yes, exactly. Phi is less than 1, so it means VD, engine capacity, is always high. For the same power output, capacity or displacement volume is always high for a diesel engine compared to SI engine. You cannot design a compact diesel engine, but you can design a compact SI engine. This is the reason why SI engines are used in motorcycle and we don't have a diesel powered motorcycle as popular as SI. You cannot design a compact engine because you are running engine with the Phi less than 1. Much 30 to 50% XSR is being used. Later on, I will discuss why. Okay, so we are using very high proportion of air for a given fuel proportion. So the engine capacity or volume is larger, much larger compared to SI engine. So there are two reasons. You are filling in more air mass and you are also operating at high compression ratio. The combination of these two will lead to heavier engine. Okay, so it's heavy weight. So this has disadvantages, mechanical disadvantage. Engine is heavy, right? So the stresses to be withstand are higher in diesel engine compared to SI engine since you have a heavier components. Okay, and you know the inertia of the components are also dependent on the weight of the component. So all these are high. So you can also say that this will lead to poor vibration characteristic. That is what I have highlighted here as another reason, right? So the NVH characteristic of diesel engines are not on par with SI engine. This is the reason why SI passenger cars are more popular than CI passenger car because the vibration and noise characteristics are poor. Not only heavy weight leads to vibration, that is another reason. Here I have highlighted noise also as a reason. Can anyone tell me why noise and vibration is higher in CI engine compared to SI engine?
Because of higher size, the reciprocating mass of the engine is higher compared to SI. So if the reciprocating mass is higher,
Larger size. Okay.
because
Because of higher peak firing process, sir.
What is it?
Higher peak firing process.
Peak firing pressure. Okay.
And
Tmax is
uncontrolled
high.
combustion knocking
Uncontrolled combustion.
is the normal combustion in CI engine.
Uncontrolled combustion. Okay.
And sir, knowingly we have a poor octane number for this fuel. So that anti-knocking quality will be very poor.
Antenna quality will be poor. But here we want a poor antenna quality fuel, right? When you say poor
Yes.
anti-knock, it means high C10.
Correct.
Because octane and C10 are inversely proportional. This we already discussed. So when this
Correct.
is low or poor, this is going to be high, but this is what I want for CI. Noise and vibration are not only due to heavy diesel engine. The other problem is the ignition in CI engine is self-ignition or auto-ignition, which is different from SI engine, wherein you discharge electric spark and initiate combustion. Here you don't have any external aid to ignite. Fuel air mixture has to self-ignite. Okay, self-ignition in a SI engine is categorized as knock, okay, or abnormal. But here the normal combustion itself will be initiated through self or auto ignition. So because of the self or auto ignition based combustion mode, suppose if the time taken for ignition is more, you will have more vibration. Okay, you will have more noise. That is what is abnormal combustion in a CI engine. So the normal combustion event needs to be carefully controlled because of self-ignition based combustion event. Otherwise, it will lead to very high noise, very high vibration. Otherwise, also even with a minimal or shorter delay, since there is some delay and then ignition happen, the fuel air mixture will undergo uncontrolled phase, as you rightly said. Initially, you have uncontrolled phase, then we get into control phase. The way the combustion even gets started in a CI engine is in an uncontrolled mode, and then it gets into control mode. Okay, so there is some phase of uncontrolled mode of combustion being experienced by a diesel engine, which is not in the case of SI engine. That's why you have a poor NVH characteristic. NVH, noise, vibration, and harshness is always poor in a CI engine because the combustion is a self-ignition or auto-ignition based combustion event. Then we have another important limitation: smoke or particulate emission are high in diesel engine. This is one of the reasons why some of the Western countries altogether ban diesel cars. They don't use diesel car because they don't want to see smoke in the tailpipe. This is something which is visible to the naked eye. Okay, they don't want to see the smoke coming out of the tailpipe. This is the reason why some of the Western countries even ban the diesel passenger cars. Okay. This smoke or particulate emission are again a problem in a diesel vehicle. In a SI engine, you don't have smoke. Okay, we are going to, in the second module, we are going to discuss about the pollutants, regulated pollutant. SI engine don't have this particulate emission. Why? Because
of lesser fuel density, sir.
Sir, homogeneous mixtures.
Homogeneous mixture.
Less carbon molecules, sir.
homogeneous mixture is a primary reason. So you have a homogeneous mixture combustion in SI engine. You have a homogeneous fuel air mixture. That's what we have discussed earlier in the SI engine combustion. You have an external mixture preparation based combustion mode. Okay, you provide longer time for mixing fuel and air because you inject or introduce fuel during the intake stroke. Okay, and ignition gets started during the end of compression stroke. You provide longer time for mixing, fuel air mixing, and fuel is highly volatile, can readily vaporize. Okay, all this leads to better mixture preparation, and you end up in forming a homogeneous mixture. Particulate or smoke emissions are resultant of heterogeneous or rich mixture. Once you have a rich mixture, fuel air mixture inside the cylinder, when I say rich, it is phi greater than 1. Generally, the ideal value of phi is around 2 to 4. I will give more detail as we move on when we discuss about the pollutants. Okay, so this is the ideal value for forming soot. Soot is nothing but solid carbon. Okay, so you need to have a rich mixture inside the cylinder to generate the soot particle. Since SI engines have homogeneous mixture, you have a phi value of around 1, or at the most max value is around 1.2. So you never get into this 2 to 4 regime where you are forming these particles. So because of homogeneous mixture and uniform phi value of around 1, 1.2, you would never form particulate in a SI engine combustion, but in CI engine, it's one of the problem. CI engines will have very high particulate. Smoke is nothing but it's a gas phase with suspended particle. That's what is smoke. Okay, soot is a solid carbon particle. Smoke will have suspended solid particle as well as liquid particle. So when I say smoke, it is everything put together: solid phase, liquid phase, and gas phase. Particulate are one of the most complex pollutant because it includes all three states of matter. There is a gas phase, there is a liquid phase, which is unbound or partially bound fuel or lube oil that will be suspended in the gas stream. You also have solid particles, which are soot, suspended in the gas stream. So smoke is nothing but it is a gas stream. The stream carries gas stream carries soot, which are solid particle. It also carries liquid particles. Liquid particles are unbound hydrocarbons. Okay, that source for this is fuel. Source for this is lube oil, lubricating oil. So you have liquid phase, you have solid phase. This is solid phase, this is liquid phase, and you have a gas stream carrying all this. You have all three states of matter when you say smoke. Okay, that's why I say that this is one of the most complex pollutant emitted by IC engine as being generated. Major component in the particulate matter is soot. Okay, I am using interchangeably particulate matter and smoke. Smoke you can visualize as a gas stream carrying solid and liquid particle. Everything put together is a particulate matter. I will give more detail as we move on in the second module. I will give this PM, but just take a note that it's one of the complex pollutant emitted by IC engine. Okay, these particles form primarily in a rich region. As I said, in the P value of 2 to 4, this is the ideal regime for forming soot particle. You get into this rich mixture, although we just now said that we are running diesel engine with XSR 0.4 to 0.8 is P much less than 1 is the overall, but local fuel air mixture will be rich in this regime to form the soot particle. The primary reason is you don't give enough time for mixing fuel and air as you do in SI engine. Reason number one. Reason number two, the fuel that we use is diesel, which is a heavier fuel. It cannot readily vaporize. Okay, you have a heavier fuel and you are giving lesser time for mixing fuel and air. You end up in getting heterogeneous combustion. So you have a heterogeneous mixture, fuel air mixture in diesel engine. This heterogeneous mixture leads to this regime, 2 to 4 regime of equivalence ratio that very well forms soot particles. So there will be significant soot particle generation in a diesel engine, and that will reflect in the smoke, exhaust smoke that comes out of the tailpipe of the engine, CI engine. Okay, this is again another problem. So these are the shortcomings of CI engine, although they are most popular because of the versatile nature, better fuel economy and lower fuel costs. You also have this problem that needs to be addressed. So coming back to the nature of the combustion event, just now I said that CI engines have self-ignition based combustion event or auto-ignition based combustion event. So what we do to initiate the combustion event, we are going to inject fuel into the cylinder by using this injector, fuel injector. You don't have a spark plug in a CI engine, right? Cylinder head will include this injector. So spark plug is replaced with a fuel injector in a CI engine. Okay, and this injector has a nozzle tip, as you could see here, and around the circumference of this nozzle, injector nozzle tip, you have a number of orifices. So here in this case, you can count that you have 3 plus 3, 6 plus 2, 8 orifices. Okay, so you have this 8 orifices spraying fuel into the engine cylinder. Right? Okay, so this is how it sprays fuel at a high pressure, very high pressure. The pressure varies anywhere between 200 to 3000 bar. 200 to 250 is the typical pressure if you have a mechanical injection system. These mechanical systems are low-cost system that we use for off-road diesel vehicles. Not vehicle, the diesel engines that we use for stationary, or the speed is not a variable in stationary engine, as you know. We use them for For example, agricultural water pumping application for farming. Okay, and we also use for standalone power generation. Those are stationary engine. They run at a fixed speed at a fixed load. Okay, this engine still use mechanical fuel injection system. On-road automotive engine generally have a flexible electronic injection system wherein you can vary pressure anywhere between 300 bar to 3000 bar, and you can also vary the number of injection pulses. Okay, you can have multiple pulses, and you have a complete control over the injection pressure, number of pulses, and timing, and so on. It's highly flexible electronic system, but they are expensive. So here you have a number of orifices spraying fuel at a very high pressure, okay, into the cylinder. In the cylinder, what do you have inside? Air. Okay, air resides in the cylinder. And when do we spray this fuel?
At the end of compression stroke.
Yeah, so almost at the end of compression stroke, you are going to spray. Okay, so once you spray, this liquid phase spray will have to absorb heat from air, because the typical air conditions will be around 30 to 40 bar. It depends on the compression ratio. Okay, 30 bar is the typical pressure inside, air pressure inside the cylinder, and temperature will be around 700 Kelvin. So 30 bar, 700 Kelvin are the typical conditions considering conventional compression ratio, but these conditions are going to vary based on the compression ratio. So you compress air to that pressure level, 30 bar pressure level, and temperature also rise due to compression effect. And you are spraying this high pressure fuel over that. Once you do that, combustion is gas phase, you are introducing liquid phase fuel. So there should be phase change from liquid phase to gas phase. For phase change, what do you need?
Latent heat, sir.
Latent heat. So you need a latent heat, okay, to convert liquid phase fuel into gas phase. And that latent heat is taken from air. So you have a significant proportion of air inside the cylinder. When you spray fuel, this fuel particle take latent heat from air, get converted to gas phase. Okay. So this is what is vaporization. And before that, when you spray the fuel, there is something called atomization. The outer periphery of the spray will start to break up. Okay, it will be like a thin film. The film will break, start to form drops. Okay, once the drops are formed, the air will go and occupy that space. It's called air entrainment. Once the air occupies space, the fuel start to evaporate. Drops start to vaporize by absorbing latent heat from air, get into gas phase. Okay, so the combustion won't start immediately after the liquid phase is converted to gas phase. What will be the next step? You have converted liquid phase to gas phase. What should be the next step to initiate combustion?
Forming of radical, sir.
Forming of radical will be the final stage. But before that, something needs to be done.
Air entrainment.
After air entrainment, you have vaporization. After vaporization,
Air fuel mixtures.
mixing. You have to mix fuel and air in the required proportion. Always remember that combustion will get started only with appropriate phi, that is fuel air proportion, appropriate T. Right? To initiate combustion, I said you need two things. One, ignitable fuel air mixture. Second one, you need an ignition source to rise the temperature and start the combustion. So once the liquid phase fuel get into gas phase, it has to mix with the surrounding air in the required ignitable proportion. So mixing has to happen. Okay, it has to reach to the ignitable proportion. Then once you rise the mixture to the ignitable proportion, and if there is an ignition temperature available nearby, okay, then the radical formation will start to take place. Once the radical formation start to take place, ignition happens. As you could see here, ignition will start to happen in the outer periphery of the spray. That is, outer periphery is here. So here you have ignitable mixture with ignition temperature. So ignition will start here, and then slowly it spreads throughout the spray. As you could see here, there are multiple spray flumes based on the number of spray that you have in the injector. The number of sprays depends on the number of orifices that you have in the injector. So this is what is happening. I inject fuel at a higher pressure. Right, it can go very well about 2000 bar also. It can go up to 3000 bar. It depends on the injection system. Okay, so you have injector mounted in the cylinder head. It sprays fuel. Okay, what you have in the cylinder air, typical conditions are 30 bar, 700 Kelvin, but it is subjected to change based on the compression ratio. Right, so you have a spray with a finite profile, and there are two important characteristics. One is cone angle, which is the included angle of the spray, and the other one is the spray penetration length. There is a maximum length at which the spray can travel inside the cylinder. That is what is spray penetration length. Okay, you have these two important characteristics, cone angle and spray penetration length. So basically, when you introduce liquid phase fuel, you have to ensure that you are exposing this liquid phase spray to the surrounding air so that these processes, whatever I said, happens quickly. So these are the processes. So we inject fuel typically at this timing, 10 to 25 degrees Celsius, before the piston reaches stop dead center during the compression stroke. Okay, that's why I say that we give limited time. So with a very short time lag, ignition is going to start. So you could see that between injection and ignition, there is a very limited time. This limited time for fuel air mixing is what is leading to heterogeneous mixture. So this is what is the primary reason for heterogeneous fuel air mixture. And that's the reason why we have smoke only from CI engine, not from SI engine. So these are the processes, as I just now said, happens one after other. So there are sequence of processes that happens one after other. One is breakup. The outer fray will start to break because the outer fray, because of the air resistance, it will be looking like a thin film. This film will start to break because of the shear force. So air is offering resistance for the spray movement, and this resistance will result in breakup event. So drops will start to form. We want a very fine drop because the drop size is going to decide the surface to volume ratio. So we want this to be higher so that you can expose this drop to the surrounding air so that it will get into gas phase quickly. Vaporization will be dependent on the drop size because it affects surface to volume ratio. So once you form the drop, the air will go and occupy this space. Okay, so there is something called air entrainment that happens. Once air entrained, the latent heat will be absorbed. There is a vaporization. Okay, so this happens one after other. So there are sequence of events. Once gas phase is formed, you have a vapor. This vapor has to mix with air and you have to reach ignitable range. So fuel air mixing is happening once a gas phase fuel is available in the cylinder. Okay, and then finally you have combustion, that is radical formation. Before that, for radical formation, what you need is Phi ignition, and then you need to have a T ignition, that is the ignitable temperature. As I said, the combustion event happens with proper combination of this Phi and T, right? And this is self-ignition based or auto-ignition based combustion, unlike SI engine wherein you have a spark discharge. And this can happen only if you have this and this. As I just now said, it's a combination of this ignitable mixture and ignition temperature. Okay, and this T ignition, that is the ignitable range of temperature, is achieved by having proper compression ratio. So the ignition event is totally dependent on the value of the compression ratio. That is the reason why we say that it is a compression ignited engine. Okay, the compression process is what is helping in igniting this mixture, fuel air mixture. Okay, that's why it is defined as a compression ignited engine. Compression ratio generally is high, well above 14. The normal range of compression ratio will be around 14 to 22 for CI engines. Okay, this is a normal range of compression ratio for CI engines, well above SI engines, almost twice compared to SI engine. That is how you reach this T ignition. Otherwise, there is no ignition, self-ignition. And this Phi ignition is the ignitable proportion of fuel and air. To achieve this ignitable proportion of fuel and air, you have to increase the relative velocity of fuel and air. I use the word relative velocity of fuel and air because here fuel is moving at some velocity. What will decide the fuel velocity?
The injection pressure, sir.
Exactly.
And density of fuel.
Injection pressure and density of fuel. So you will have, because density affects the inertia. Okay, so injection pressure is a primary parameter that affects the velocity of the fuel. What will decide the velocity of air?
Suction pressure.
what will decide the velocity of air? So you have turbulence or how you shape the combustion chamber. So this is where the combustion chamber shape will come into picture. We discussed about squeeze and swirl that you generate during the compression event. Squeeze is radial motion and swirl is based on the piston shape. Okay, it's a rotational motion that is based on how you shape the piston top or crown. So you create this motion, air motion. If you don't have air motion, if air is stands still inside, okay, it will create problem. What problem it will create, I will tell. So you have to create appreciable air motion. Okay, that depends on the combustion chamber shape. You have to create swirl, you have to create squeeze. Then only there is air motion. There is a fuel motion based on the injected pressure, fuel pressure. And there is an air motion based on the shape of the combustion chamber. So you need to increase its relative velocity. Please note that whatever event I have just now discussed, all this happens with a very small time scale. Millisecond, microsecond, or even nanosecond. It depends on the engine running speed. Engine running speed will decide the total cycle time. And whatever events we are discussing are happening during a fraction of the total engine time. Okay, all these events are a fraction of the engine operating time, total operating cycle time. And one cycle time is based on the engine running speed. So it's very, very small time scale that we are dealing with. Within this time scale, all these processes has to happen quickly, one after other. So increasing relative velocity of fuel and air will play a significant role in CI engine combustion. Okay, that's why we need to inject at high pressure. We need to create appreciable air motion through swirl and squeeze inside the cylinder. Okay, so suppose if you don't create appreciable air motion, what problem will be encountered in the engine? Suppose you are spraying fuel at some pressure. Okay, let us assume that the air is not moving. Okay, you are not creating any swirl or any squeeze inside the cylinder. The fuel is sprayed. Okay, air is not moving in. What will happen because of this? From a combustion perspective, what problem will be encountered?
So mixing will be even bad actually.
Mixing is not going to happen. If mixing is not going to happen, what problem will be encountered? How the combustion event will proceed? So outer periphery of the spray will undergo, because of the shear force, it will undergo breakup. Okay, so we are assuming that air is not moving. Okay, but whatever air available in this space, the fuel vapor will take heat from that. It will get into gas phase. Since there is some air available in this space, it may get into ignitable range. Okay, and you have compressed air available in the cylinder. Let us assume that you have a ignitable temperature and you have a ignitable mixture around the periphery of the spray. So once this happens, ignition is going to happen. Okay, so there will be ignition, combustion will get started. But once the combustion started, you will have products of combustion. So the fuel will be surrounded by its own product of combustion if the air is not moving. Okay, this is called choked condition. So the fuel in the core region will get choked because it is surrounded by its own products. Okay, the combustion event is not going to sustain. Even if it gets started, the fuel in the core region get choked because the products of combustion are not moving away. Unless otherwise there is an air motion, this won't move away. So what we want is this products have to move away. Fresh mixture has to enter into the spray region. Okay, this has to happen. So that's why it's very important to create an appreciable air motion so that air goes continuously and fill in this space. The products of combustion leave from this space. Okay, so creating air motion inside the cylinder plays an important role. This is one of the reasons why CI engine combustion is also referred to as mixing control combustion event or mixing limited combustion event. Mixing control or mixing limited combustion event. Unless otherwise there is an appreciable motion, unless otherwise there is an appreciable fuel and air motion, unless otherwise there is a mixing, there is no combustion at all. Okay, in a CI engine. So overall combustion event can be referred as a mixing controlled or mixing limited combustion event. This is different from SI engine combustion, wherein we said that it is overall event is referred to as a flame propagation based combustion event. Clear?
Yes, sir.
So here we said that we have a heterogeneous fuel air mixture. There are two equivalence ratio considering the heterogeneous mixture. One is called global or overall equivalence ratio. This we measure outside the engine. This is based on fuel proportion and air proportion that you measure. Suppose if you do a experiment on the diesel engine, you always keep track of how much of air is going in, how much of fuel is going in. You are metering that. You are measuring it using a device. So based on the device, that overall fuel quantity and air quantity that you get in, you are defining this ratio, global or overall equivalence ratio. It generally is a lean condition, 0.4 to 0.8. It is in a range because you are controlling. How do you control load in a CI engine?
By amount of fuel injection.
Yes, so you are controlling load in a CI engine by varying the injected fuel mass. Air mass is constant. In a CI engine, you are varying this fuel mass in order to achieve the variable load. You have a fixed air mass in the cylinder. You are controlling fuel mass through your injection system. Suppose if you at low load, you are going to run with low fuel quantity. At high load, you have to increase the fuel quantity because you want more power. So the power you get, you are controlling by controlling the injected fuel mass that is going to control the energy release, thermal energy release. Okay. So you are controlling load in a CI engine through controlling the injected fuel mass. Air mass is constant. That's why you have a range of equivalence ratio, global ratio. It varies anywhere between 0.4 to 0.8. In terms of air fuel ratio, these numbers are given. Again, these are typical numbers. It is anywhere between 18:1 to 80:1. What is stoichiometric air to fuel ratio for diesel?
14.7.
It's typically around, what is it?
14.7 approximately.
14.7. Yeah, around 15. Okay, 14.7, around 15. That is the stoichiometric value. Now here you could see that the actual value varies anywhere between 18 to 80. So this is much lean. So you are using very high air proportion. It's much higher than the stoichiometric proportion. So that's why we say that it's a lean burn combustion. Okay, and this is different at different load. Full load you have more fuel mass. That's why there is a less value. No load you have less fuel mass. You have a higher value. Nevertheless, it is very high air mass. Okay, typically the air quantity will be around 30 to 50% higher than the stoichiometric proportion. That is nothing but excess air. So you use around 30 to 50% excess air. Okay, this is based on global value. There is another ratio, you call it as a local equivalence ratio. This local equivalence ratio can vary anywhere between 0 to infinite. Okay, anywhere between 0 to infinite. What is 0 and what is infinite?
Zero means like no fuel available, and infinite is no air.
Exactly. So 0 is nothing but you have only air. There are regions in the combustion chamber which doesn't have any fuel at all. Then the equivalence ratio local value is 0. You have regions in the combustion chamber wherein you have only fuel, you don't have air at all. Okay, so you have, remember the fundamental definition of Phi, you have defined it based on actual fuel to air proportion divided by stoichiometric fuel to air proportion. Okay, these are the regions which do not have any fuel, only air is 0. These are the region you have only fuel, you don't have any air. So it is infinite value. Okay, so local value can vary anywhere between 0 to infinite, and it is a function of space and time, location. Inside the cylinder at different location, you will have a different Phi local value. Global value is constant, whereas local value is a variable. It depends on the space, that is the location inside the engine combustion chamber. There will be distribution of Phi value. It varies anywhere between 0 to infinite. It's also a function of time. Time here in terms of crank angle. At different crank angle instant, you will have different value of local Phi. So Phi local is a variable which is a function of location inside the cylinder, it's also a function of the time in terms of crank angle. Okay, so phi local is variable, and this is where you have a problem because the pollutant formation is dependent on local phi rather than on global phi. Okay, and the problem is if you want to run CA engine similar to SI engine in the equivalence ratio of say 1 to 1.1 or 1.2, you are going to have a very high smoke formation in the cylinder because local equivalence ratio with rich region will shoot up. Beyond this, there is a threshold limit of global value. If you go beyond that, you are going to have a very high rich regions inside the cylinder because you have a limited mixing. That is a problem. You give limited time for fuel air mixing, you end up in forming more and more local rich region if you try to increase this phi value beyond 0.8. That's why you need to keep it well below 1. You have to ensure that you have sufficient excess air available in the cylinder. Otherwise, you will have a problem of very high smoke or soot emission from the diesel engine. Okay, so the overall global value, max value, is fixed based on the consideration of minimizing the soot particles emitted from the diesel engine. Okay, so that is how it works. You have this two values you have to deal with, global and local value. Clear?
Yes, sir.
So this is all about the overview. The next thing we need to look at is the different stages of CI engine combustion. So similar to what we have done for SI engine, here we are looking at the stages, how the combustion event happen in a CI engine. We are looking at in terms of stages. So this is how we characterize this combustion event. Okay, so I will show the typical pressure profile and heat release profile and come back to this heat release profile. So this is a typical pressure profile of a CI engine, okay? And then this is a typical heat release profile. You also have something called a injection rate shape profile. This is the injection rate shape that shows how the injected fuel mass vary with the time in terms of crank angle. X-axis, what you have is crank angle. This TC is top dead center. Compression TDC is a reference point, right? And you have different angles. The angle before compression TDC is marked with the negative sign. Angle after compression TDC is marked with the positive sign. This is a standard nomenclature for indicating the angle, crank angle. Okay, so you have this reference point, and this is a pressure profile. This is a heat release profile. This is an injection profile. So injection event gets started here. It's over here. The combustion event gets started here. So you could see that even after the start of combustion, the injection event continue to happen. This is how a normal CA engine combustion is taking place. You are injecting fuel even after the start of combustion. So you start to inject here, you are ending here. In between, the combustion event gets started. Okay, this is where the combustion event gets started. And in order to characterize this event in terms of number of stages, we need to take heat release profile because this clearly shows the different stages of combustion compared to pressure profile. We have done this analysis with pressure profile in SI engine. In CI engine, it's very difficult to identify different stages using pressure profile. That's why we need to take this heat release profile in order to identify the different stages of combustion. So here, when you look at this heat release rate profile, the combustion event happens in CI engine in 4 distinct stages. Those 4 stages are indicated here. This is stage 1, ignition delay time, between start of injection to start of combustion. Combustion gets started here. Then you have a second stage, premix phase combustion, that is from here to here, which is a premix combustion phase or premix phase combustion, which is based on the delay time. So once based on how much of delay time is happening in a CI engine, the second phase, subsequent phase, is to be the duration or the intensity of this phase is dependent on the delay time. When there is more delay, there will be more intense premix phase. We use the word intense. If there is a less delay, there is going to be less intense premix phase. So this phase follows delay time. So the intensity of this phase depends on the delay time that is encountered in a CI engine. So you have delay, ignition delay time, premix phase combustion, followed by mixing control combustion phase. Okay, so mixing control combustion phase. This is also called diffusion phase combustion. Mixing control or diffusion phase combustion. That's the third stage. The final stage is afterburn stage or late combustion stage. So you have 4 stages: ignition delay, premix phase, mixing control, then late combustion or afterburn phase. These are the 4 stages. It's time up. I stop here. I will continue, give more details about these different stages in the next class. If you have any questions, I can take your questions now.
So one question I have is like, even if we have this fuel with a very good acidity number, even then premix combustion phase will exist over there, or it will be very stringent.
It will be less intense. So you cannot have a 0 delay time. You always have some delay time. Did you get what I'm saying? You always have some delay time. You cannot have a 0. If you have a 0 delay time, you won't have any premix phase.
Okay, I got it, sir. I got it.
Okay.
So basically, the premix combustion phase is the function of delay time. Higher it is, the more intense it will be, right, Mr.?
Exactly.
Okay.
Okay. Any other questions? If there are no questions, I stop here. I'll meet you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.